So we'll start with the covering space theory. Okay. So, so I'll talk about this covering space theory in a more general concept. So let X be a topological space, X bar be connected Hausdorff space, and and a function rho such that x tilde to x be a map be a continuous onto, let us say, let us say this property only. Okay, so in this case, so I will write some definitions. So okay, so rho is called unramified slash or unbranched. So there are some conventional names. Unbranched slash smooth covering. Okay. In literature, it is known as these kind of names: unramified, unbranched, and smooth coverings. Okay. Of X, if if rho such that X tilde to X is locally a homeomorphism. Okay. What does it mean? That is, for every point P belongs to, let us P tilde X tilde, there exists a neighborhood, let us say in X tilde. Just wait a minute. Okay. In X tilde such that rho restricted to this neighborhood such that tilde to rho tilde is a homeomorphism. Okay, so such thing is known as uh, unramified covering, and in this case, so in this case, we denote, we say, so jointly we say that this is smooth covering, and X tilde is smooth covering space. Covering space of X. Okay. So here is some exercise which we can do. Means I will leave it as an exercise only, but it is easy to check. Okay. So the first thing is, uh, so in definition, one, Rho is basically, you can show that rho is an open map. Okay, so this is quite easy to see. Okay, so okay, so let us look at this thing. So suppose you have a covering, let us say this is x tilde, and you have a covering P, and this is your x. Let us say you have given a point uh, P tilde here, okay, and a curve starting through P tilde. Okay, so this should be rho. Okay, so you have some curve here starting from this one. So if so this is if x tilde belongs to x tilde such that rho of x tilde is equals to x, we say basically x lies over x. Sorry, x tilde lies over x. Okay, or we can also say like x is a projection of uh, x tilde cover x, or x tilde is, yeah, x tilde cover x. Okay, so here is your point x tilde. Okay, and this is a curve passing through this one beginning at x tilde. So now you will get a curve rho of gamma. Let us say this is gamma and this is your point x. So you will definitely get a curve in x, okay, starting from x. Okay, let us say this is gamma tilde. So let us say this is gamma. Now the question is, what about going backwards? So precisely it means that, so now the natural question is how about going backwards? Okay, so what does it mean? It means that suppose you have a point x here. So I mean, it means that suppose gamma is a curve starting, gamma is a curve in x starting from x belongs to capital X, and if x tilde lies over x, that is basically rho of x tilde is x. Okay, so the question is there a curve gamma in x tilde starting at x tilde such that rho of gamma is basically this gamma? This is question. So I mean, you take a curve, you take a curve in x starting from some point x. You collect all those points which are the pre-image of x under rho. Can we always find a curve gamma starting from these x tilde so that rho of that curve gamma will give us the gamma in x? So this is the question. Okay, so if the answer is yes, so if the yes, we say curve curve gamma has been lifted to gamma, or also curve gamma is continuation along gamma from x naught to z, whatever the x is. Okay, so this is the question. Now you'll see some examples where we don't always have a lifting. Okay, means I mean to say that lifting is not always possible. Okay, so let us look at this example. Okay, so example 1. Okay, so so let your x is z such that so, z belongs to C such that mod z is equals to 1 and x tilde be the curve gamma. So I will write what is this curve. So, okay, so uh, this is your unit circle. Okay, and the curve. So this is gamma. Okay, and so this will be sorry. So this is x. This is your x, and the next curve which I will draw is like this. Okay, so this is your x tilde. Okay, means gamma. So I will write in red. Okay, so this is the thing, how to define a map. So we define a map as a radial image. So I mean the so we want to define a function from rho x tilde to x. So you take any point x tilde, let x tilde belongs to x. Okay, so rho of x tilde is the intersection of line joining x tilde to origin, intersection of line joining x tilde and origin, x tilde and origin to the unit circle. Okay, so I mean to say that you take any point x tilde here, you join the line, and this will be your x. Okay, so this is the function. Okay, now since this is a radial map, you have some properties of rho. So rho is continuous, obviously on to. I mean, this will cover every point because the way I have drawn this curve gamma. Okay, so rho is continuous, rho is on to, uh, rho is open. Okay, so I am giving this example uh, where rho is not a smooth covering. Okay, so smooth covering by mean that it is locally a homeomorphism. Okay, so you can check that rho is continuous open, rho is open, but rho is not a smooth covering. Okay, because what happens is if you take any point here, Okay, and you take a neighborhood of this point. Let us say this. So uh, okay, now in this neighborhood you have these arcs. Okay, so for these arcs, like if you if you if you join this point to this one, this image will be this one, and if you extend this one, it will hit this one. So for this point also, so x1 tilde and here x2 tilde both have the same image here. So this cannot be locally homeomorphic. Okay, so it is not a smooth covering. Okay, let us see another example. Okay. So again, in this case, your x is z belongs to C, such that mod z is equals to 1, and x tilde is any curve, be a curve as follows. Okay, so again I will draw the, so this is uh, your circle, and the curve will look like this. Oh, sorry. Okay, so this is your curve gamma. Okay, just wait a minute. Okay, so this is your curve gamma. Now again the function is defined in the same way. So define rho from x tilde to x in the same way as defined in example 1. Okay, so now again first is rho is continuous, also open and onto. Okay, also second thing is rho is smooth covering. This you can check. Okay, but now you don't have the lift. How? So the thing here is that let me see this one. Okay, so you consider this function. So sorry. So basically for lift, we have okay, so you take any sub arc of this one. Okay, like this. Okay, and so what would be the image of this? So like what you have to do, where the curve this ends, you have to take, you have to start from here. Okay, so now what would be the lift of this one? Okay, so just wait a minute. If it take this arc, uh, yeah, so here is your origin. So okay, So this will be image here, any point x tilde to x. Okay, so we need to find a curve gamma which will start from x tilde so that it will map here, map to this curve. Okay, so observe that this curve has this direction, and if you want to take this curve, it will have this direction. So it will be this curve. Okay, and this will be this curve. Okay, so now if you take a arc, like let us say, suppose you take a curve like this, okay, from here to here, which is starting from x. Now from x tilde, uh, so you take this curve gamma. Okay, so let me write it down. So you take this curve gamma, okay, from here to here. Now rho inverse of x is x tilde. So we want to prove that this curve, which is gamma starting from x, has a lift. Okay, but this is not possible because the only possibility is the only possibility for a curve start from x tilde is either this curve or going through this curve. But again, if you take these curves, image of this one under rho, so they will lie on this one, okay, but it will end here. So this part will not be covered by this curve. And if you take this curve, these things will come, these parts will come. So again, this doesn't have any lifting. So but the curve gamma does not have lifting. Okay, so this is an interesting example. So this says that the lifting is not always possible. So the question, so in this case, but if lifting exists, that will be unique. So what we have, so let us just write this theorem. It says that, so let rho comma x tilde be a smooth covering of x. Suppose gamma is a path. Suppose gamma is path in x with initial point x naught. So as we have seen that in a smooth covering space, lift not necessarily exist. Okay, but here we are proving that if lift exists, then this is going to be unique. Initial point x naught, and let us take rho of x naught tilde is basically x naught. If there is a lifting of lifting lifting gamma of this one from x naught tilde, then this lifting is unique. Okay, so the proof is not that much hard. So suppose there is another lifting. There is another lifting, let us say sigma of gamma from x naught tilde. Okay, so So basically row of sigma is basically gamma, and also row of this is gamma. So our claim is basically this gamma, sorry, this sigma is basically equal to gamma. Okay, this is our claim. So what we are going to prove is, so what is this sigma and gamma? So this is from A to B to x tilde a, and this gamma is also from, let us say. So these are the parameters of this curve. Okay. Now consider the set T. So T belongs to A comma B such that sigma T is basically equals to gamma T. So basically our claim is to prove that T is basically your A comma B. Okay. Observe that T is always non-empty. T is always not equals to 5 because because A belongs to T, because both is starting from x tilde. Okay. Now next we prove that T is closed. This is quite easy since sigma and this gamma both are continuous. Okay. Next thing we will prove that T is open. Okay. So T is open. This follows from, one can check. This follows from the fact that rho is locally homeomorphic. Locally, okay. So now since E comma B is connected, and T subset of A comma B is both open and closed. Therefore, we have T is basically equals to AB, and hence this basically. So we prove that if at all the lift exists, it is going to be unique. Okay. Okay. So the existence just wait a minute. So existence of lifting can't be guaranteed, okay, as we have seen in example 2. Therefore, we define a new class of covering. So in the literature, it is also have different kind of name. New class of covering. Okay. So which is, so let me write the definition. So this is definition 2. So a smooth covering space rho comma x tilde of x is said to be this also has different kind of names: unlimited slash unbounded slash regular covering if every curve gamma in X with initial point X belongs to X can be lifted to a curve gamma with initial point X tilde, where rho of X tilde is X. Okay, so for every X tilde means, so you have a curve gamma in X with initial point X. Now you collect all the pre-images of X. Okay, so you should always have a lifting gamma with initial point of that pre-images. Okay, so this is the definition of regular covering. So we now consider the following problem. Following problem, which is basically given X, describe all unbounded, unramified coverings of X. Okay, so unramified means smooth covering. Here we have already defined. Okay, so we put a condition. So this is known as condition A. We will denote it as condition A. So let X and X, so X tilde and X is as previous. B, so we are defining a map with the following property, and we'll say that this is condition A. B such that for every P belongs to X, so every P belongs to X has a neighborhood VP such that rho inverse VP is union of disjoint open sets in X tilde. Okay, that is basically rho inverse VP is nothing but the union of U alpha. So this is the disjoint union where, so U tilde alpha is open in X tilde. Okay, this is there, and restriction of rho on each of these open sets is a homeomorphism. Homeomorphism onto VP. What does it mean? That is row restricted over U alpha tilde. So this is from U alpha to this. VP is homeomorphism. Okay, so in this case, basically these are called distinguished neighborhoods. Okay, and VP is called fundamental, which is evenly covered, is properly okay. Okay, so here's the proposition. This is let rho such that x tilde to x be a function which satisfies condition A. Then we have the following. First one is rho is one can prove rho is continuous onto and open map. Okay. Second thing is rho is locally homeomorphism. One can prove the third one is every fundamental open set is connected. Okay. So proof is so one can go through the proof. For proof, one can go through the. This is also in lecture notes. Convey chapter 9, proposition 7.2. I'm going to go through this one. So these are the properties of this one. I mean, proving this one and this one is rather easy. You don't have to do that much. Okay. So keeping this in mind, okay, so let us look at example, which is one can verify this thing. So example, so this is a remark. Example of smooth covering which does not satisfy condition E. Okay, so this is let your x tilde be z belongs to C such that z is not equals to 0 and argument of z is in between 0 to 5 pi by 4. Okay, and x is basically your c minus 0, rho of z is basically your z square. So then rho such that x tilde to x is on to. Also one can check rho is locally homeomorphism because derivative 2z is non-zero in x tilde. So we know that if a conform if a holomorphic have if a holomorphic map has non-zero derivative, so it is locally 1 1. Okay, so rho is locally homeomorphism. Okay. Now let delta r is equals to xi such that xi minus I is less than r. So for any r you can define r in between 0 and 1. Okay, so you need to check this one. So rho inverse delta r has two components. Okay, so so two components, let us say v1 and v2. So one of these components, so rho restricted over v1 from v1 to delta r is homeomorphism, but from another component v2 to delta r is not a homeomorphism. Okay, that is rho does not satisfy condition. Okay, now we mention the main theorem. Okay, so now we can provide the solution to problem 1, which I will write in the following theorem. Okay, so if rho such that x tilde to x is a smooth covering, then following are equivalent. Okay, then the following are equivalent. So rho comma x tilde is regular covering. Second is rho satisfies condition A. So basically we have characterized when we have a lift. Okay, so for the lifting, this property is the characterization. If rho satisfies this property, condition A, you always have the lifting, and if you have the lifting, rho will satisfy this property. So this is a good, I mean, this is an important result. Let's see a note. So henceforth, uh, in view of proposition in this theorem A, the covering, so by covering I mean rho satisfies condition A. So henceforth, in view of proposition and theorem A, we shall use the condition A for the definition of covering space. Okay. So some examples are as follows. So these are some examples. Following are some examples. So let f such that c star to c star defined by fz is equals to basically z square. So then f c star is covering. Okay. Also you can take f such that c to c star defined by fz is equals to e to the power z is a covering. Okay. Third thing, you can take f such that c to c fz is equals to z square is not a covering. Okay. Fourth thing is f such that, I mean, you can create a lot of examples. One defined by f of t is equals to e to the power 2 pi iota t. Okay, then fr is a covering of this gamma. Okay, now we will. Okay, so the next thing what we want to discuss is this is the monodromy theorem. This is one of the most important theorem in the covering space theory. It is the monodromy theorem. Okay. Okay, so suppose we have x tilde and x. Okay, and you have a covering map rho. Okay, so you take any point x, okay, and a curve which is joining x to y, and a curve this gamma. Okay, so now this has a lifting from x tilde to some, sorry, this curve gamma has a lifting from x tilde to some y tilde. Okay, let us say this is gamma cat. But now the question is, how does this y tilde depends upon this curve gamma? Okay, so the question is, if you take any other curve, let us say sigma, okay, uh, let sigma be any other curve starting 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 from x and ending at y. Uh, so again, this sigma will also have the lift sigma tilde. Okay, so sigma tilde has sigma tilde is lifting from x tilde. What can we say about the termination point of this sigma tilde? So is it y tilde, and when it will be y tilde? So can we say y tilde is the termination point of this one also? So this is not always true, okay, but the monodromy gives the answer to this one. Okay, so let me state monodromy theorem. Okay, so it is so the monodromy theorem. Okay, so this is let rho comma x tilde be a covering of x, and let gamma and sigma be two paths in x with same initial and final point, or let us say terminal point. Okay, let gamma tilde and sigma tilde paths in be paths in x tilde with same initial point such that gamma tilde and sigma tilde are lifting of gamma and sigma respectively. So our question is whether this gamma tilde and sigma tilde terminates at the same point. So for that one, this is the condition. If gamma is homotopic to sigma, then gamma tilde and sigma tilde terminate at the same point. Moreover, gamma tilde is homotopic to sigma tilde. Okay, so one can find the proof in any in any book on this topic, which covers the covering space theory, because this is an important theorem. So let us see the following corollary of monodromy theorem. We have the following important uh, the proof is quite easy. So if x is simply connected, okay, and rho comma x tilde is its covering of x, then rho is a homeomorphism basically. X tilde to x is a homeomorphism. Okay, so we'll try to prove this one now. So, observe that we only need to prove that rho is 1 1. So we only need to prove that rho is 1 1. Okay, so for this one, assume x1 tilde comma x2 tilde belongs to x tilde such that rho of x1 tilde is basically x2 tilde. Okay. Okay, so let gamma tilde be path in x tilde from x1 tilde to x2 tilde. Okay, so what is this? Means that gamma tilde is from this parametrization tilde such that gamma tilde of 0 is x1 tilde and gamma tilde of 1 is basically x2 tilde. Okay, now in this case let us consider this one, row of gamma. So this is x is basically a closed curve. Okay, and since x is simply connected, gamma is basically homotopic to a constant curve. Homotopic to a constant curve. Constant curve. Let us say x naught only. Okay. X naught. Let us say sigma. T is basically x naught. So this is basically kind of, this is your x tilde, this is your rho, and this is your x. Okay, and this is your x naught, and this is your curve gamma, and let us say this is your curve sigma. Okay, so, sorry, this is your this one, or we can also write this as, let me write this so that we don't have to use that much notation. Now you just have to use the Monroe theorem. Okay, so here is your x1 tilde. Okay, now this is homotopic to this one. Okay, and basically gamma tilde is lifting of basically gamma. Okay, and just wait a minute. So this row of x1 is, and basically this you can also take row. So basically row of x1 tilde is equals to x naught, which is nothing but row of x2 tilde. What we have assumed. This one we have assumed. Okay. So now this is the case. So you just take a constant path x1. Take the lifting of this constant path x1 tilde. So the sigma t is lifting of, okay, this one. Now we have this gamma is homotopic to sigma, and gamma tilde and, okay, so gamma tilde and sigma tilde is lifting of gamma and this one respectively. Okay, so they have the same terminal point. Now the terminal point of sigma tilde is x1 tilde only. Okay, because it's a constant curve, and terminal point of this one is x2 tilde. So it means that by monodromy theorem x1 tilde is basically x2 tilde. So this is 1 so means it is a homomorphism. Okay, let us now talk about this not uh, uh, lifting of continuous maps. So this is lifting of continuous maps. Lifting of continuous functions. Okay. So definition is let x comma y z be domains in C. Okay, and let f such that y to x and g such that z to x be continuous. Okay, continuous maps. Again, this also definition is same as that one, previous one, lifting of curves. We say that a map g tilde from z to y is a lift of g with respect to f if f composition g tilde is basically g. That is, the following diagram commutes. We have y to x and we have z to x. So y to x we have f, g we want to define from z to y. So this is your, so this diagram should commute. Okay. Okay, now the question is, does lift always exist? Okay, and this is also not true always. So the question is, does lift always exist? Exist. Okay, so basically the question is, if f says that y to x is covering, okay, it means that this is your y and this is your x, this is the covering f, okay, is covering, and g says that z to x is holomorphic. Okay, so and you have some domain g, this is holomorphic. Okay, can we always find a, so does there exist g tilde from z to y such that f composition g tilde is basically g? So the answer is no. So let us take fz is e to the power z. So f is from c to c star and gz is your z, which is from g from c star to c star. So the possibility of g tilde z is nothing but log z, which is ln mod z I capital argument of z. So, g tilde is from c star to c star, but g tilde is not continuous on c star. So you cannot always have this lift. Again, mod Ohm theorem will give the answer for this one. So this is done. So we have seen some theories on covering spaces and some problems, fundamental problems. Okay, now we'll solve some one or two problems. Just wait a minute. Yeah. So let me see the problems now. So we'll do one problem. Okay. So question one is this one. Let f such that d to c. This problem will be on Little Picard theorem, holomorphic map, such that f of 0 is equal to 0, f dash 0 equals to 1, and mod of fz is less than equals to 2 for every z belongs to d. Okay, then which of the following is less or true? Okay, so the A is, first option is, if fz is basically z plus summation n equals to 2 to infinity anz to the power n, then mod an is less than equals to 2 for every n greater than equals to 2. Okay, option B is mod fz is greater than equals to 1 by 12 for every z belongs to C is C is a curve, so that mod z is 1 by 4. Option C is given W belongs to this ball, there exists Z belongs to this force such that Fz is equal to W, and the D option is this ball is contained in basically the image of the unit is under F. Okay, so let us solve this problem. So let us write Fz is equals to Z plus summation n equals to 2 to infinity anz to the power n. Now mod fz is basically mod z minus summation n equals to 2 to infinity anz to the power n. Let us say this is equation A. Now let us talk about option A. So an we know that 2 pi I integral over mod z is equals to r fw upon w to the power n plus 1 dw, where r is between 0 and 1. So mod an okay, so mod an is basically 1 upon 2 pi, and integral over mod z is equals to r modulus fw upon w to the power n plus 1 dw, which is less than equals to 1 upon 2 pi into 2 integral over mod z is equals to r mod dw upon r to the power n plus 1. So this 2 comes from, okay, so mod fz is less than equals to 2 for all z belongs to d. Okay, so this will hold. Okay, now what is this? So this you will get mod an is less than equals to 2 upon r to the power n, as r tends to 1 minus. Okay, so this will be mod an will be less than equals to 2 for every n greater than equals to 2. So the basically the first option is true. Okay, now let us look at the option B. So this is your set. Z says that mod Z is basically 1 by 4. So summation of an z to the power n is less than equals to summation mod an mod z to the power n. Okay, and this summation an z to the power n is again less than equals to, because mod n is less than equals to 2 for all n, so this will be 2 summation mod z to the power n. Okay, this is B. Now by equation A and B we have, so equation A is basically, yeah, so using equation this one, okay, so this we have, so minus will be, so this minus, so minus will be basically greater than equals to minus 2, so this will be, so mm, sorry, mod of fz is greater than equals to mod z minus 2 into summation mod z to the power n, infinity. Okay, which is mod of fz is less than equals to, now mod z is 1 by 4 on this C, so this we can write this one minus 2 summation 1 by 4 to the power n equals to 2 to infinity. So this will be basically 1 by 4 minus 2 by 12. So this we will get fz is greater than equals to 1 by 12 for every z belongs to C. So this is also true. Option B. Now let us look at the option C. Okay, so let W, let us say any W naught belongs to this ball. Okay, so it means that mod of W naught is basically 1 by 12. Okay, on the circle we know that, so on the circle Z says that mod Z is equals to 1 by 4, mod Fz is basically 1 by 12. So now let us write Zz of this one. So mod of W naught is basically mod of Fz. Okay, for every Z belongs to C. So by just wait a minute. So by Rauch's theorem, zeros of G is basically zeros of F in this ball. Okay, that is, there exists Z naught belongs to this ball such that F of Z naught is basically W naught. Okay, so C option is basically, this is true. Obviously, if you have this ball, this is going to be contained in F of D. Why? So this we have already seen. If you take any, this one, you have a point Z such that it is an image of that point Z. So this one is quite trivial. I mean, you take any ball, this one, and point in this one. You have a point in this one such that this W, so W take in this one, you get a Z, so that W is the image of this Z under F. Okay, and this ball is always contained in D, so this basically is contained in F of D. This is also true. Okay, so we are done with the today's assignment. So there's an update which I want to tell. So there will be an extra class. Uh, so maybe NPTEL will inform you regarding this. So we'll meet in that extra class. Okay, so I will end the session. Thank you so much, everyone.